Turn my microphone back on, and it should come up okay. I think I have the stream on. I think I have the stream on. All right. Well, this is Understanding Bitcoin Source 17, talking about transactions, and I just realized the screen is not correct. Definitely not that one. Yeah, why isn't this, what screen is this showing?
Alright, I'm on Twitch. I see a background of a farm.
Yeah, I don't know why, because it's like, is this desktop? No, what is this showing?
It's showing another desktop.
Yeah, like I have no idea. Is it this desktop too? XAT? No. Do I have to? Okay, well, this is not what I
Go to
want.
OBS.
I am in OBS.
Okay, and what is OBS displaying? Sorry, not making it today from Prem. What's sats, yo people? Yo.
Yo. Huh. Method, window capture. Nope. Display capture. Yeah, it just kind of works usually.
Can Alright, I see.
All right, you know what? I just add a new media source because this
Yeah, create a
happens.
new media source with that screen.
Yeah, every time it seems there's always problems. Screen capture. Okay, yet another one. Display. Okay, okay. Well, see, this one's getting my screen, and I wanted to get my screen. It's just acting up today. Built in. Maybe I'll just present from my screen if I can't
If
get
you
this.
could just do the whole screen rather than a specific.
Yeah, usually it's fine. It's just today it doesn't want to cooperate. So displays. Yeah, okay. Look, I'm gonna put this here. Okay.
There it is.
Yeah,
Okay.
it took a little bit of fiddling for whatever reason.
Transactions.
Yeah, transactions, and let's put me under. All right. Transactions. Next slide. Where do we start? Where do you want to start?
So what's a Bitcoin transaction?
Yeah. Well, I like to get definitions straight first. So I decided to define what a transaction is in the English language. And what better way to do that than a dictionary definition from Merriam-Webster? And a transaction is something transacted, especially an exchange or transfer of goods, services, or funds. So I like to do a ground up approach and think about how do we physically transact currency. And these are the ways that I think that we physically transact currency. We give the currency we have on hand to our intended recipient. We delegate payment to an entity we trust. And we, like sending to a friend who will forward to our recipient. We delegate payment to a process we trust. So like sending money via the mail or using a bank. But these are typically ways that we physically transact currency, pretty much in person, or we're going to give it to a friend or like some institution that we trust to do it because of some process, right? Like we trust the bank to send our money because if they don't, we could file a lawsuit and we have the state violence to help back up our claim. So how do we digitally transact currency? You have anything, Roz?
Well, if we use these ledgers, it's everybody updating, getting the ledger digitally or broadcasting using computers.
Yeah, ledgers are a way to digitally transact. I was thinking more in like a general sense, like if you wanted to send money to someone, even pre-Bitcoin, how'd you do it? You'd like, yeah, how'd you do it?
You would mail them an envelope.
Okay, that's a way. How'd you do it digitally? Yeah.
Digital.
Yeah.
I don't remember what it was like.
Well, we have Venmo, right? We have
Oh
PayPal.
yeah.
We have Cash App.
Okay.
So, and I try to make this a general thing. So, I was gonna ask, do all the ways to physically transact apply? So we give the currency we have on hand to our intended recipient. Typically, we don't really do that digitally because well, it's very easy to make copies of a certain type of data structure. So it's not really, we can't really give it on hand to somebody else because these things aren't very hard to create. Um, we could delegate payment to an entity we trust, so sending to a friend who will forward to our recipient. Is there a digital equivalent of this? Yeah, I guess we can delegate payment to people, but even this is like kind of, it's really a process, not an entity. Or I guess an entity that follows a process. So sending the money via the mail using a bank. We also make digital transactions, logging into our bank account, picking a recipient, and giving them some amount of money. So it is important to note that for these processes, we don't trust them to perform our payment, but we do trust them to act in their best interest. So like I was saying with banks or other institutions, we trust them because there's some kind of reactionary measure that we can take if they don't do what we ask. So really we're just asking that they act in the best interest, which is operate as a business, collect revenue, profit, and if they perform poorly, then retaliated against by the government. So, what is needed in a transaction for an intermediary to perform payment because it is in their best interest?
An incentive.
Yeah, since an incentive,
Yeah,
right?
yeah.
So you always need some kind of incentive, and the best alignment of incentives can be found. Well, what is needed? What is needed? Oh, yeah, digital transaction. I was gonna go over these different questions, but yes, incentive, and the same thing for digital transaction.
Yeah, it doesn't matter if it's digital or not.
Right. Yeah, you need to have some type of incentive to make sure that they're doing things in their best interest. Um, yeah, so like what is needed, I think it'll be better explained as we go over the perfect incentive alignment system, or a very good one at the very least, which are Bitcoin and Bitcoin transactions. So here's some QR codes for reference. The original Bitcoin source code. I know sometimes my camera blocks video
This
code.
one can be scanned.
Yeah, so it's all around my face.
Oh,
Because I think it's more interesting if we look at the original source code, and a lot of people are interested in looking at this from like a historical standpoint. So transactions all start with a version number. And I'll wait a little bit. Yeah, hey, how's it going?
Well, we are on stream.
Yep, just talking about Bitcoin transactions.
Okay.
Yeah, I was saying it all starts with the version number. Version numbers are really interesting because, well, first I could say what version numbers are. So Bitcoin transactions have a version number on them, but version numbers in general are values within a data format that stays in some fixed position between data versions. So any system that has data that changes has an implicit version to it, especially if it's used with the same system. Was that knocking or why?
I did hear some knocking.
Okay.
I don't see any messages.
Okay. He's gonna check. Anyone there? Oh, I see. He's having some trouble with the button. Huh. No? Okay, that might have just been next door. Yeah. Yeah, so version numbers, some piece of data within the data format, the overall that is indicating explicitly what version it is, other than it being something implicit in a system. And when I say fixed, I mean the nth byte or bytes will always represent the version number. So IP, packets, they, for example, have a version number, and most protocols that are developed, especially on the internet, have version numbers to, help facilitate upgrades. So all evolvable systems with a dependency on data presented by third-party actors can benefit from a version scheme. So dependency on third-party actors means the system relies on entities who cannot be coerced to keep the system alive. For example, in Bitcoin, we're entities that cannot be coerced to keep the system alive. We use it because we want to use it, and the system relies on people wanting to use the system. So a version scheme allows systems to evolve gracefully because it can be used to quickly distinguish an unknown data format from being outdated, new, or malformed, which can help a lot when parsing, and you get some efficiency gains. So if you think driver's license, uh, there could be even cases where malformed or forged data gets punished. But if you indicate that this is a certain version that's not understood by the system, there could be better ways to gracefully handle your request. So this is again taken from the original Bitcoin source code because I thought it's best to look at the original format for things. And yeah, you can see right here int n version. Int in C++ is just means a number, an integer, and it takes up 4 bytes. So that's the first part of the transaction. So what are some basic components of a digital transaction? Now that we have the version out of the way, like what other things might we want from a digital transaction? I feel free to chime in if you have anything to say. The question. Okay. It looks like a shoebox.
Who you're sending money to.
Yeah, exactly. Where you're sending money to, like maybe like some balance or some way to show that you have money to some system, right? So here are the basic components that I defined. You need some identifier for the recipient that you're sending money to. You need an identifier for the sender. You need a specification of a quantity for an amount being transferred. And you need some credential authorizing the spend. And I'm saying like authorizing the spend from where? And a larger system should keep track of the state of accounting, which is the blockchain in the case of Bitcoin transactions. Blockchain contains the accumulation of all transactions processed in the Bitcoin network. So you could always tell who has what. And as you know, if you have a full node, the way you validate a full node is by downloading all the transactions that have ever happened and updating this state of accounting called the UTXO set. So let's go into the identifier for the recipient. What is that? So whether we should define the recipient or sender first may seem like a chicken and egg problem, but in Bitcoin, a recipient gets paid without a sender, or alternatively, an implicit sender through the Coinbase. So you don't always typically need a sender. There is a way to get paid through the system, which is how money's created. When Bitcoin was first made, Satoshi was mining blocks and administering himself Bitcoin because he was playing by the rules of the system. But there wasn't really a sender. He was just claiming as per the rules of the system. Our recipients are identified in Bitcoin by code, essentially. It's written in Bitcoin script, and it's specified in a part of a transaction labeled the script pub key, which is a word that I use a lot. It just has code for a locking script. And then most programs contain a public key and ask for a signature from the corresponding private key to complete successfully. This is what we know. What we say, protect your keys. Your keys are the things that you use to spend, and all of that, is very important. So the original version of Bitcoin only allowed recipient identifier programs that would just check the signature corresponding to a public key. This was pay to public key check. I don't remember why I put these little square brackets here. So yeah, this is an identifier for the recipient. Any questions? No? Okay, next slide. Oh, and I wanted to show in a transaction, it's stored in a place called the vout. And if you've programmed C++, a vector is like a list. So it's like you have things called arrays, which are fixed in size, but a vector is dynamic. You could push back and put more things in there, and it reallocates automatically within your memory. So you have essentially a list of CTX out. These are a definition of a data structure. And then you have, you labeled this list of outputs and you call it vout. So again, this is original Bitcoin source code. So what does CTX out look like? Since we're talking about recipients, we should know what the structure of a CTX out looks like. And if we zoom into it, we see that there's 2 values here. One that says int64, which indicates a 64-bit value. It's pretty large. And then we have something called a script pub key, which is of type C script, which is again just like code. And C script is bytes, but they have a lot of helper functions in that class. So this is where the recipient identifier program is stored. So if you want to ask for money from somebody, you will give them an address, and the address typically has a way to construct a script pub key for the sender. And again, these are like programs that you ask them to send to, and the money gets locked into a program until you want to spend it. So recipient script pub key. So what is the end value? And as you can imagine, in an output, you have a recipient, and what you were saying before, like
How many coins you want?
yeah, and exactly, your coins, how the amount. So defining the end value leads us to a specification of a quantity for an amount being transferred. So this is an amount denominated in sats that will be transferred to the recipient, and the amount is defined on each output, and there are 64 bits allocated for this number. 64 bits can represent a max value of 1.8 E plus that to the whatever 19, and the total number of satoshis that exist is 2.1 E plus 15. So it's more than enough to represent the total number of satoshis that you could send in a transaction. Yeah, and this number is 21 million times 100 million because every Bitcoin is 100 million sats. Yeah, and these bits seem like they're pretty small numbers, but when you add up more and more bits, you get bigger and bigger numbers. And even when we talk about 128 bits, it's very hard for humans to understand the scale of the size of number 128 bits can hold. So now we can go back and think about the sender. So we know how to create a recipient. When Satoshi's mining these blocks, putting Bitcoin into circulation, he was putting his recipient information and validating his Coinbase transaction to give himself money. But now if he wants to send it, he has to give some identifier about who he is. And this is like a username for a transaction, and the credential to spend is like the password. So an identifier is needed for the system to know where to transfer the money from, which requires a check to see if you have enough, and an invalidation to disallow a future spend with the same funds. So you have to prevent double spends, right? You also have to have an identifier for the sender. And an identifier for the sender is actually a reference to a previous transaction that's saved as part of the blockchain that specified a program that only can be spent with the current sender. So when I make a transaction, I'm identifying myself as a sender by pointing to the program with an output of a program that I specified in the script pub key. So the identifier for the sender in this case is our input, is what we call it. And our inputs reference another transaction. So really, we point to the output of a transaction to say this is who we are. This program is us. And this is stored in something called the vin. So we have, again, a vector, which is like a list that's dynamically sized. And it has elements called inputs, ctx in, and this is labeled the vin of a transaction. And just like the vout, but it's always more interesting if we look inside of the transaction input. So here's the interesting, we have something called prevout. So this is where the previous transaction is referenced. What information do we put in the prevout? It's pretty much two pieces of information. We put the transaction ID that we're referencing, that we have funds in, and we have the output. So a transaction has multiple outputs. Again, we have this list, and you have to specify which index your output is in. So that's in the C out point. I didn't I don't think I put the whole thing here, but just know it has a transaction ID and it has the index number of the output that belongs to. So now we can go into our credential authorizing the spend. If recipients are identified as code for a program written in Bitcoin script, then the credential authorizing the spend would be information that allows that program to return a successful result, right? So since most scripts are checking for signatures corresponding to a public key that was set in the program, the credential in most cases is a signature. That's how I can prove that I own an output from a transaction with a certain program that's asking for a signature. I give that signature. The data needed to validate the script goes in the input in a section of the data called a script sig. And we can see a script sig here. And this change was SegWit, but these are legacy transactions. Again, for someone who maybe wasn't watching, all this is from the original Bitcoin source code. I like going back to basics because it's just easier to explain that way. So this is where the information needed to spend the recipient script goes in this thing called the script sig. So you also have,
Do you sign it in there, or like,
yeah, your signature goes in here.
you need to sign the whole transaction, so do you sign, do you like,
There's certain parts of the transaction that you sign. Yeah, you don't necessarily sign the whole transaction.
okay.
Yeah, we could go into signature hash as we continue, but yeah, the signature goes in here
Alright.
into the inputs.
Cool.
Yeah, the transaction ID, by the way, was maybe that's what you're thinking of. Transaction ID hashes more of the transaction, and part of the motivation for SegWit was any value you put in here gets put into the data that's hashed to make your transaction ID. So when people used to put signatures in here, signatures are like somewhat malleable. So if you could change a signature, it would change the whole transaction ID, but still remain valid. And that was a problem, yeah, because
Alright.
we like consistency. Yeah, and then we have unlock time and end sequence, and these had interesting qualities in the original Bitcoin source code. So the lock time was originally a property on a transaction specifying a block for which a transaction shouldn't be mined before. So if you had like a lock time, then you wouldn't get your transaction relayed or mined, essentially. And that's what lock time was used for in this original Bitcoin implementation. And all this was like rehauled, and I'll go over that. But end sequence was like a version number for a transaction input. So if a later transaction wanted to replace an input, it would have to have a transaction that has all the same prev outs in its inputs as the old transaction. So like if I had input I wanted to respend, I'd have to make a new transaction with that input and all the inputs it was spent with the first time. And then, yeah.
Maybe. If there's no cheese in it, sure.
Oh, that's right, cheese. Yeah, yeah.
Ordering one.
Yeah, yeah. There'll be more. Yeah, if a later transaction wanted to replace an input, it has to have the same inputs. And then you need to have at least one sequence number higher than the lowest sequence number on the old transaction. This is like a weird rule, but yeah, you have to have a sequence number that's higher than your lowest on an input of the previous transaction. It was weird logic in general, and this didn't really work. It was, yeah, because again, like this happens to do with replacing a transaction. You don't really replace transactions in the blockchain, and this has to do with not relaying or including a transaction to be mined. But none of these are quite like consensus rules. So can you maybe think of what problems we'd have with just these lock time and sequence? Or like, do they have to be respected at all, right? Like if the lock time is stopping transactions from being relayed and mined, but really only within the code. It has nothing to do with blockchain validation. So I could take a transaction with whatever lock time I want, go and try and mine it in a block, and it would not be respected. I mean, it would, like, yeah, the original source code rules would not be respected, and the blockchain would be respected. So these are policy things that they weren't helpful for consensus validation. That's why these were very buggy. End sequence, similar thing.
Was that end sequence for like the replace by fee kind of thing, or?
Yeah, end sequence was a way for replace by fee, and I think they also were making payment channel implementations for it. But in this version, it was just like policy, and that's why it was bad. It was very crappy, and it was removed, and it just moved out of it. And yeah, here I was showing the problem with end lock time and end sequence. So in the original source code, Bitcoin miners used to be represented as a function in the Bitcoin client software. So it was just like bool Bitcoin miner. Bool is just like a boolean. It returns that. The name of the function is Bitcoin miner. Took no arguments. And then this is when they'd like collect transactions. You'd do this for loop, and it would go through this thing called map transactions. And as you can see, if it's like a Coinbase, then you don't need to go and add it to your collection of transactions, because this is going to be manually constructed by the miner. And if the transaction was not final, then you'd continue. So you'd go through whatever is at the bottom of this loop and come back. You'd essentially skip it. So in the mining code, it would ask you to skip it through this code. But if you looked at the blockchain consensus logic, there's nothing that would know that something is completely final or not.
Okay.
So, yeah, all these can be respected. Um, yeah, and lock time didn't really need all that big of a fix, but because you just add consensus validation to it, and sequence needed a bigger fix. And Peter Wulla had this Bitcoin Stock Exchange comment that I thought was very convenient to add in. The old end sequence semantics, where non-funnel transactions were held in the mempool until finalization, were not only a bandwidth issue, but also a memory problem. I believe that was the original reason for removing it, long before the mempool got an actual bounded size. So he was just saying this is a memory issue. But there's also like a bandwidth spam issue of being able to replace a whole bunch of transactions. And as some may know now, there's like rules to doing things. Then end lock time, we ended up introducing this check lock time, verify opcode, allowing transaction outputs to be encumbered by a time lock. When the CLTV opcode is called, it will cause the script to fail unless the end lock time on the transaction is equal to or greater than the time parameter provided to the CLTV opcode. This is from the Bitcoin wiki. If you've ever been on here, it's like bitcoin.it something. And since the transaction may only be included in a valid block if its end lock time is in the past, this ensures the CLTV-based time lock has expired before the transaction may be included in a valid block. Okay. Is currently used in CLTV style payment channels and time locked fidelity bonds. So yeah, like I said, end lock time was pretty good. Didn't need that many changes, while it hasn't evolved like a crazy amount over time, whereas end sequence has, because we found that being able to replace inputs with a set of requirements was necessary for, again, these memory issues and for it not to be spammed. So if now replace by fee has certain rules, like, hey, you have to have a bigger absolute fee than the original transaction, and certain things with the fee rate and whatnot.
Is there a limit on the mempool, like max size or something?
It could be as big as you want. There's no one mempool, so everyone could change their mempool as they please. So you could make it really big. You make it a gigabyte big. I know someone who has a really big mempool who has very old transactions that were collected in that big mempool.
Wait, so if you go back a slide, what is he talking about there?
Huh?
Long before the mempool got an actual bounded size.
Yeah, now there's a default size for mempool.
Okay.
Yeah, but you can make it as big as you want. There's a default size that's put into the code.
Okay, so now everybody has a default, whereas maybe back in the day it was like whatever.
Right, yeah, back in the day they didn't have like any default limit, and you should always have some sanity checks. But then if that issue's fixed, then you have this bandwidth issue where you can spam the network with a whole bunch of new transactions.
And the default was pretty low, right? Like 300 megabytes or we're way past that these days.
Yeah, I think that's what mempool.space shows is 300 megabytes, but they have a bigger one. That's how they're able to tell you how big. End lock time and sequence. So some end sequence stuff. Note that in order to set a relative lock time, the transaction must have the following properties. A version must be 2 or greater, and sequence must not have 30-second bit set. There's all these like random rules, but there was a lot of tweaking to the end sequence to allow it to work safely in Bitcoin, and it didn't just appear to work the first time around. Okay, I don't need to read all this, but just to show you. SegWit. So I didn't really put much for SegWit because I have an example of transaction serialization that I was gonna hope demonstrates what a SegWit transaction looks like. So I was just gonna go into, again, the serialization. Serialization in Bitcoin means the encoding of data into bytes. So
Is that base 58?
uh,
Or no?
Base 58 is an encoding, but here serialization is more like you have like a class in a programming language, whether it's like Scala or JavaScript or Rust, and you want to find a way to put it into bytes such that I can give it, it's standardized, and I can give it to you, and you could parse those bytes whatever language you want.
Right.
So this is like the transport format, I guess would be a good way to put it. because internally all languages have like classes, instructs, and whatever stored in their own way.
Yeah.
So when you serialize it, or when you try and get the bytes of it, it might not be the easiest to parse in other languages. So serialization deals with almost like a transport format. How can we define something that everyone knows about and can parse easily in whatever language they want? These are kind of small text, but I'll read them out. So here you have a version number, or actually what might be more interesting is if I were to show you the transaction first for this. So let's see if I could go and pull that up. Where is this? Oh, okay, it's all over here. I'm gonna X out of this because I have the transaction here somewhere. Oh, I want this thing to go away. This is, all right. I have the link here, but it's not letting me select it, so my nav bar is, okay, finally. Okay, it's right here. So this is a transaction I serialized, or I took the serialization of and decomposed it. Anything interesting here? So this has a Coinbase transaction for its input, because you might be wondering, how does a transaction look? If it's a Coinbase transaction, like, is the input still made? The answer is yes. One input, and we'll see how that looks like. This is a pay to taproot output, and this is a pay to witness public key hash, and this is an op return. And I'm just gonna show you how the bytes look like in hex and break down those bytes.
Can you zoom in a little bit?
Yeah, for sure. Oh, let's try Command plus. Yeah, Coinbase and all these outputs. So going back here, I know the text is kind of small. I don't know if this, so okay, that works. So this is the version. The version is 2 on the transaction, and we should be able to see that up here somewhere. I think has the version. Let me know if you see it. Do they not have the version? Okay, they do. I just missed it. Version is 2, right? And again, the first thing you have in a Bitcoin transaction is going to be this version, so you know how to parse the rest of it. If you remember, the version is an int, which is 4 bytes in C++, and this is in hex, so every 2 characters represents 1 byte. So this should have 8, right? 8 characters because it's 4 bytes. 1, 2, 3, 4, 5, 6, 7, 8. This is how I parse. I literally had to like count and then just press the enter sign. This is a version. Count and blah, blah. So SegWit, I was gonna explain some of the changes here. SegWit, usually you'd have the size of your inputs first, but they wanted to break, if you had Bitcoin clients that were stupid and didn't try and ignore version 2 transactions, they might try and parse it as a version 1 transaction. And people did not want that happening. So what they did instead is they said, let's try and trick old nodes and just say there's 0 inputs. So it's always gonna be invalid. Just like something they did. And then you have this thing for like the SegWit flag, and I could even show the code afterwards and we could look at back and forth. So yeah, this is one of the small changes made to SegWit, and you'll see the other changes that we make. You have the size of your inputs. Again, we have the Coinbase transaction. So, did I just edit that? There we go. Coinbase transaction. This is the input 1 transaction ID. So even though there's no actual input, like there's no previous transaction that was made that of output you're spending, you can reference this 0 transaction ID. None of this is like validated, right? It's a Coinbase transaction, but you still have the input because you need to specify the amount that you're getting.
Does
So
Coinbase need to be the first transaction?
Huh?
Does the Coinbase need to be the first output?
Yeah, in your like the first transaction that
Or first, yeah.
to you don't have to claim the Coinbase, but like pretty sure there needs to be a Coinbase in a block. But we could validate that also. I'm pretty sure, but I'm not 100%. Like
But if
90.
you have that 0 there, then it feels like you could just put it like last or like in the middle. And if the input is all zeros, then
No, we definitely don't need like this transaction ID since there's no reference, there's no 0 transaction. But to keep consistency with data format in Coinbase transactions, you do reference this previous transaction, even though there's no previous, right? It's making Bitcoin. or it's issuing Bitcoin. Input 1 output index, again, set to the maximum value. Why? Because there is no index of a previous transaction you're making or issuing this Bitcoin. Input 1 script sig size. So we do have a script sig. And why do you think we have a script sig? And we can see it here. So 03A. The endianness should be the same here, I think. 03A, blah, blah, 5516. 03A, 55, yeah. So why do you think we have a script sig here? You have
See
any-
who owned the, well, hold up, in the Coinbase? So,
Yeah.
I mean, I guess that's where it's going.
Yeah, none of it's validated, right? Like I mentioned, you have to put some information that satisfies the program of the previous output, right? But this doesn't have a previous output, you're issuing Bitcoin. So the script sig is just like random data that you would put inside of it. Why might you want to put random data in? Because the nonce space is pretty small. So you could exhaust the nonce while you're trying to mine a block. And one of the things that you do when you exhaust your nonce is you could change 1 byte in your script sig and have a completely new nonce space. So none of this is validated. This is essentially just used to help mine. Yeah. Witness 0 and sequence, yeah, again, set to whatever because.
Is that the only way they use to change the nonce if you want to update your nonce because you tried mining and you didn't?
No, there's other things you could do. Like the block has a timestamp on it. Again.
Oh, the timestamp. Yeah, that was the one I was thinking of.
Okay, yeah. So and you could like change that, and no one's gonna really notice or care, because old blocks are allowed after or like you could have a block that's dated before the block before it, because there's rules that are kind of fuzzy for time. Anyway, this is the input. This is how Coinbase input looks in bytes. Put whatever you want. And then we can go to the output. So the first thing you have is the size of the outputs. In this case, we had 1, 2, 3 outputs, right? And then in these 3 outputs, the first thing you have after the size of the output is you jump right into the first output, and then you have an amount. Oh my goodness, this is an amount. An amount has 64 bits, I'm pretty sure I said, and 64 bits is 8 bytes. So these should be 16 characters. And again, like if you ever parse these, you could go and check 1, 2, 3, 4. This should be half, and it is, right? So yeah, we have 16 characters represent 8 bytes. So it seems like a small, number can be represented, but it's actually pretty big. So yeah, output, first thing that comes is the amount, and then the second thing that comes is the size of your script pub key. So like this is 22 bytes, for example, a little lengthy here. So this should be 44 different hex characters, and this should be your program. What is the output 1? We can go and look at that. Output 1. So because we are in SegWit v1 and not SegWit v0, again, v1 taproot, this is a tweaked public key. That's what this thing represents. So you actually can't see the script here. You'd have to go and provide like a Merkle proof, when you actually spend it. And same thing for this pay to witness public key hash. This is going to be a hash, right? Okay, output 1 script pub key. So now we go into the second output. Again, we already said how many outputs we have, so we don't need to like do any other delimiters per output. We know it's always going to have an amount, the size of script pub key, and then script pub key. So here we have the output 2 amount, we have out 2 script pub key size, and then we have the out 2 script pub key. Out 3 amount is 0, right? It's op return. So that's why this is very easy to see in hex. The zeros is going to be the same in decimal as it will in hex. And you see some op return data that they try to render that clearly didn't come out looking very nice. And that script pub key size was 26. Okay. And the hex for it. Next slide. Okay, so we also have something called the witness stack, and I'm glad that the Coinbase transaction still included like a witness, because it's not needed in like the semantic sense at the very least. And the witness is placed at the very end of a transaction. So even though when you have a segue output and you spend it, the witness needs to be provided in your input, is what they say, right? In quotes, it's like part of your input. But it's actually sort of the end of your transaction over here to almost like make sure to delimit it as something that's completely separate from what's going to get hashed, right? This is more like an efficiency thing, and semantically, you don't want your witness grouped in with your previous inputs because all of that information needs to get hashed and made into a transaction ID. And one of the motivations for having a witness is to keeping this separate, so you can have non-malleable transaction IDs. Yeah, so you're always gonna have these things, right? Like the witness at the end, and it goes by like the inputs that you have. So again, you don't need any delimiter for this. This is a witness for one input, and a witness isn't just like one element. You have something called a witness stack, which contains, it's like a list of data items that you push onto the stack, and then this should be witness size. And then you have your witness here. Or is this witness size? Yeah, this is the size of this first element of your witness. And then you have your lock time all the way here at the end. And all right, pop quiz, This pop quiz isn't super informative, but I just put it in as a fun thing. So do transactions have timestamps? Anyone know the answer to this?
Transactions
Depends on who
themselves.
you
I'm gonna
ask.
say no.
Yeah. No. Yeah.
Blocks?
It doesn't. Yeah. Definitively. Blocks do. Transactions do not. So another interesting factoid, as I was mentioning, a friend who has a very big mempool. This person said that they were able. Well, they have a big mempool and they save everything that ever entered the mempool. So they have transactions from years ago, and because transactions don't have timestamps. This kind of goes into the next one. So actually, I'll finish the story with this other question. Do transactions have expirations?
No.
No, they don't. Yeah. So
You
if
can't cancel them.
no, you exactly. You have to spend it. Right? That's the only way that you cancel it. You have to use it in another in some spend. So going back to the story. Oh, I see. Sorry, there was. I just see some chats. Ysats, hello, and I see Prem, but Raz was. Maybe shouted them up. Old, yes, I see. Okay, thanks, Prem. Do transactions have expirations? Yeah, they don't. So the friend I was talking about has a big mempool, and he has a whole bunch of old transactions from years ago. And if he really wanted to mess with people who thought that their transactions got lost to the abyss because people's mempool weren't very big, he could take a transaction, see if the output still exists, and spend it and move money out from under people's feet. So when the moral of the story here is, if you ever broadcast a transaction and it doesn't get mined, it doesn't mean that transaction will never get mined. If it only needs one person to see it and to rebroadcast it at an ideal time where the fee rates are low and the mempool is relatively empty and your money will get taken. So the best way to make sure that transaction is invalidated is to spend the original source of the funds. And this is exceptionally bad when I pay you and I think it didn't go through, so I pay you again with a different input, and then you were able to collect that first one because they had a huge mempool, and you rebroadcast it and take more
Only
money
if
from
you did
it.
a different input.
Yeah, only if I did a different input.
Most of the time, can you control the input that you want to send somebody? I guess not.
There's coin control in some wallets. Some do it like in an automated fashion, and some wallets won't even let you spend that input because they see it's in an unconfirmed input. So it won't let you before we had RBF, for example, right? It's not going to let me replace my input. So this is an issue, probably more so before. Now I can just RBF and put whatever fee I want, but so they don't have expirations. That was the end of this one. Can a transaction have a zero valid output? And this was also in the presentation. Op return. We had that zero value output. You don't need any values for your output. I could even just show it again.
Wait, what does that mean? Burn a coin or something? Or?
No, you're not burning any coin. You just have an output that isn't sending any money.
Well, you're burning the input.
The input, but this input, this is a coin. Oh, so this is a special case. This is like a Coinbase. they are allowed to spend like other outputs.
Mhm.
Yeah. Whereas like there are other rules to spending an op return when you just do it through policy. But there's nothing consensus-wide that stops you from having however many outputs you want and however many op return like outputs if you wanted to have those.
Well, so I mean, yeah. So you don't have to burn any Bitcoin. You're just paying the transaction fee, I guess.
Right. You're just mining. You're just adding data. Yeah. I guess you're
Okay.
removing opportunity costs from yourself. Because some miners, like I think RSK merge miners might have like multiple op return outputs. And again, policy will limit you to have one, I think, op return. So yeah, this is using the first transaction has a lot of special edge cases that are weird. Like I showed, having a witness for the Coinbase, even though you're not spending, any script. So yeah, zero valued outputs, they can, especially for miners, like you said, they can forego fees or like opportunity cost. I mean, this is a transaction that I just went over, put a screenshot of it, but I also had it live. And then some closing thoughts, because it's almost 7:15 anyway. And Bitcoin is an evolving system designed for change, again indicated with that version number. Transactions are as complex as they need to be and hide the majority of its complexity in script. So I'd say the most complex part of like Bitcoin transactions are the scripts that you lock your transactions into, that the spender then needs to put their script sig or witness information for. But this is what most of the debate is centering around right now: covenants in script or having more opcodes. And a lot of complexity goes in here, the script. But in general, everything's pretty straightforward, I think. And if you're interested in learning more about transactions with some hands-on programming experience, I did want to plug Lisa's course. She has a company called Base 58, Nifty Nye. It's a transaction course on Udemy. I think she put on Udemy. And yeah, I think this is LARP material, right? So
Yep.
also made this LARP thing that we could try out. And yeah, I didn't have any other thoughts. Anyone have anything to say or questions, closing thoughts?
Check out Base 58.
Yeah, this whole thing was an advertisement. No, but she has a pretty good course. I like to support her educational efforts. Yeah, all right. If no more closing thoughts, then I guess I'll.
Talking about that C++ code, I guess they had a convention where you put C in front of a class name, right?
Yeah,
And
that.
VN is because it's a vector.
Yeah,
Yes.
yeah. Inputs. Yeah,
Okay.
yeah. And V and exactly.
Alright.
There was there were semantics to put certain letters in front of certain variable names for a data type indication. Like you said, C is a class, right? You V a vector, and you have like N for like these numbers, N lock time, and N sequence. Yeah, so good observation. Anything else you want to say before I
I
end
would
stream?
rename N value to like sats.
Ah. Yeah, but
Maybe
Love the sats.
yeah, and obviously Satoshi didn't use stats. In fact, we can see what he actually used real quick.
Didn't think of it.
Was it pennies or?
No, it was Raz knows what they used because he was trying to bring back.
Coins?
Yeah,
Coins.
yeah, coins were used. Did I not put the link? Do I have?
Coins with
Oh,
a
okay, I
Z?
did. I was like, did I?
No, just coins, but it was referring to sats, not to Bitcoin, whole Bitcoin.
Yeah. Main.
Bring back coins.
I think it's in main. On. Nope. 100. It might be in the header file. I don't know where it is in here. Main.h, as you can see, first commit. It wasn't always on. There we go. Coin.
Cent.
Yeah. All caps.
Yeah, cent is a bigger denomination, but yeah, this is our 100 million. 100 million. Cent is, I don't know what this is. Is this what millisat is? I don't know. But yeah, we had different.
No, cent is 0.01 Bitcoin.
What is there a name for that? And
I mean, it's 10 millibits.
millibits. I don't know
it's
what the.
Bit cent.
Okay,
if you
I only
like.
know
I
sats.
mean, yeah, I mean, these are not really used by anybody, so.
Yeah.
Nobody needs a 0.01 Bitcoin denomination.
Yeah.
He was thinking in terms of dollars and cents, obviously, but
It
no.
would be
Or,
centibit.
you know.
Yeah. I mean, should we go back and use cent as a way?
I mean,
Oh, Prem says it's not millibits, it's centibits. Milli is 0.001 Bitcoin. Thanks, Prem.
Yeah.
I'm voting against decasets. I will hear out anything else.
Yeah.
Decasats to me is to Star Trek.
Decasense, it does sound very Star Trekky, yeah.
Decasats, rather, if you're trying to.
I kind of like Decasats.
I think the average person doesn't know Deca as a you know.
Yeah, well, you know,
Yeah.
in Ethereum they decided to do like 18 decimal places instead of 8.
Yeah, they have the Gwei,
And
right?
then they created Gigaway.
Yeah.
Like, so you
And that
adding
doesn't
another
actually-
9 spaces back. Huh. Okay.
Yeah.
Sure, why not?
Just make it bigger and
Sure,
bigger.
why not?
How many coins though? Yeah.
That's all people really want to know, right?
Huh? Well, yeah, coin here was a different number entirely. It's
People who
these
don't even know
stats.
how to ask questions about Bitcoin will ask how many coins.
Yeah.
It's just that is.
Show them this, the source code, 100
Yeah.
million. They'd
How
be
many
like,
coins? 2.1
yeah.
quadrillion.
Yeah.
That's how many.
Yeah, exactly. The total coins. Coinbase maturity, as some people know, you can't spend Coinbase until 100 blocks later. But yeah, anything else anyone wanted to see again before I close out the stream? It's the original source code if you want to check something. I didn't go over or CTX in. I didn't have what this looks like, but you know we can briefly go through this 5 minutes just so you can see what it looks like. Remember I said there's a reference to the previous transaction ID in a transaction. That's how you point to say, hey, I'm spending this right now in my input. So the C output point is in your CTX in, which is a transaction input. Contains this hash. This hash is the transaction ID to the thing you're pointing at. This N is the index of the output that you would like to spend from that transaction. It's specified with the hash. Another thing that I didn't include in the screenshot in my presentation is the C script class. Is this defined in this file? Maybe not. It's defined somewhere else. Oh, it might be in script.h. Script. Oh, let's check. But remember I said it's kind of just like a wrapper to help manipulate bytes. Yeah, there we go. Yeah, it's just got some like helper stuff here. Push UN64.
What does push do? Is that what you call to sign something, or?
Oh, it's an operation. He's putting this N, he's pushing, let's see, what is he? Pushback. This thing inherits from a vector. So he's calling pushback on this vector with N plus like this, pretty much an offset of an opcode is what he's doing. Yeah, push UN64. All right, what was do you overload this? What's the difference here?
Oh, int versus int.
No, okay, I see. It is overloaded. Yeah. Anyway.
7-Eleven on 7-Eleven, make a wish.
Yeah. I wish for 21 million Bitcoin. Yeah, all of it.
Well, you already have it.
Yeah.
Check your note.
Yeah. All right. I'll check when I get home. So yeah, the vector, and these are chars. You know, use characters in C++ to represent bytes because one character is a byte. And yeah, this is what C script looks like. You had big num, which is you know exactly what it says, is a class that represent big numbers, and nothing too crazy here. You use these overloaded operators, you know, like that you'd use for something like cout to go and add things to your vector of C script, which is that list of data items. And again, your C script is code, so you're putting things into like this program, you know, defined by this code that's held within this vector. And yeah, all right, enough of that.
How do you push your signature on this? Is there some opcode for that?
You could put it in as data, right? Like all of there's operators for unsigned characters, and you could just put these like shift it in, right? I mean, there's other overloaded things. You went 160. You have to find the right one.
I guess you could have multiple signatures in this thing.
Yeah, I mean, multisig wasn't enabled when Bitcoin first came out, and pay to script hash was a way to have arbitrary scripts. So pretty much you couldn't do multisig in a relay prohibited way before pay to script hash. So yes, it allows you to push multiple things in multiple signatures if you're doing multi-sig scripts. But in the original Bitcoin, you didn't have multi-sig scripts available for use. It was defined in the language of Bitcoin script, but policy prohibited, you know, the usage of non-standard,
So
non-standard
the original
scripts.
code had that as like that vector anyways?
Yeah, to push.
Like a view to the future.
Yeah, exactly. Yeah, to push arbitrary data items because he had the whole language defined, even though he didn't have support, policy-wise, to relay these.
Oh wait, when you're pushing, are you pushing this random scripts or are you pushing like?
Script sig, you usually put data in your script sig. Technically, you can perform opcodes in a script sig, but that was changed, and they made it to be only push only. So you can only do data pushes from the script sig. And there's like a lot of bugs that you avoid when you do this. For example, one of the big bugs that I've mentioned before is that one of the things people used to do in the script sig is they used to put, well, actually this is a little bit different, but it's a way that you could arbitrarily use data to like psych the Bitcoin network out. But your script pub key is that program that you use to lock it, your Bitcoin, and your script sig is what you provide when you're trying to spend the output. And what people would do is they'd look at for a script pub key out on the network that's unspent, and in the script sig, they'd define, hey, I want to do a data push that's as big as a script pub key. So you could trick Bitcoin into treating that locking script as just arbitrary data because you put a directive in your script sig to say ignore the script pub key. It was a pretty bad bug. And what they did to fix it is they said instead of putting the data right next to the script pub key and executing it all at once, let's look at the script sig, execute that, and then look at the script pub key and then execute that with whatever was on the script sig left on the stack. So before you'd have the script sig combined with the script pub key, now you have the script sig, you executed it, and really all you bring is whatever was pushed onto the stack. In the stack, there are no operations. The stack only has data. But that's part of the script. Maybe, I've had script presentations before, and I don't want to get too deep into that. Yeah, anyway, I think I'll have to stream. It's 7:15, and we have some food. And if not, you could let us know, and you'll get some food ordered. So, and BitDev's about to start too. 15 minutes.
15, the break.
Right.
Yeah. So if you're watching, you come by. But yeah, thanks for watching, and this video will be uploaded somewhat soon. So, see you guys.